This buoyancy problem is about calculating the draft of a floating body, also called the submerged depth or the fractional volume submerged. This example problem will use a truncated cone floating in water, but the same process could be used for any sort of ship or buoy. And calculating the draft of a ship may be different based on how much load it's carrying. And there's a lot of waterways that aren't super deep. And so large ships need to make sure that they can actually get in and out of port safely without hitting the bottom. This morning, your TA woke up and chose violence. He knows once I get recording, I stop playing with him on his treadmill, and you can see that's all he wants to do right now. So his plan was to set up this problem using English units, since he knows how much we hate them, so that later on we'll take a break from the English units and go and play with him instead. Let's at least get started. So we've got a truncated cone with a 16-inch outer diameter on top and an 8-inch diameter on the bottom. Total height 12 inches, and what we're trying to find is what is the submerged depth? What is this distance h? Again, this is also called draft when talking about ships. How deep does the ship go underwater? That's its draft. So this is a buoyancy problem, and every buoyancy problem is a force problem, and every force problem requires a free body diagram. And since we weren't given material properties for this problem, we'll have to make a few assumptions. Since we're using English units, let's choose a density of water of 62.3 pounds per cubic foot. And of course, I called this density. Technically, it's specific weight. Force over volume is specific weight. Density is mass over volume. But in English units, the units of mass are going to be slugs or pound mass. And I really can't emphasize this enough. Don't ever use slugs as a unit. If there's any way to avoid it and just use pound force instead, do whatever sort of conversions you have to do at the beginning. Go straight to pounds, because you know slugs isn't going to be part of your final answer anyway, and it's just going to mess you up. So we're starting with specific weight of water, 62.3 pounds per cubic foot, and that's pretty typical for room temperature. Since I drew this picture in Inventor and colored it using white ash, we'll look up the properties for white ash and find 39.83 pounds per cubic foot for wood, which seems reasonable. It just needs to be less than water so that it will float. Buoyancy is a force. Every force problem requires a free body diagram, so that's the first step. We draw a free body diagram. Weight of the wood is pointed downwards, and the buoyancy force due to the water being displaced is pointed upwards. A sum of forces in the y direction gives us the buoyancy force minus weight equals 0. And the buoyancy force is equal to the weight of water displaced, so we've got a weight of water is equal to the weight of the wood. And then we'll replace weight with specific weight times volume. And now here's where this problem starts to get a little bit tricky. If this were just a box, calculating volume would be very easy. Base times width times height. If the cone were a full cone, the volume equation is kind of similar to a cylinder. 1/3 pi r squared times the height for a full cone. But what about for a truncated cone? All right, it looks like Indy's actually starting to play without us, so let's call it break time. All right, back to work. So one way to calculate the volume of a truncated cone is to calculate the volume of an entire cone and then subtract the smaller cone that's cut off the top. Now, we aren't given the height of the full cone, but you may be able to tell since we have the two diameters, you can sort of extend the lines upward and figure out how tall the original cone must have been. Since if the diameter has shrunken in half with 12 inches of height, then it would shrink again the other half with another 12 inches. So this cone actually started off with a full height of 24 inches before half of it was cut off. But if we're looking up equations anyway, there actually is an equation for the volume of a truncated cone. So 1/3 times pi times the height of the truncated cone times the small radius squared plus big radius squared times the two radiuses multiplied together. It's a weird looking equation. No one would ever memorize this, but if this is a homework problem and you can Google it and look it up online, that's not too tough. So we know the entire volume of the wooden shape, so we can plug in numbers for the volume of the wood right now. We've got the depth of 12 inches, a small radius 4 inches, large radius of 8 inches. Get to a volume of 1,407 inches cubed, but since the specific weight is in feet cubed, we do have to do a conversion and divide by 12 cubed to get this into feet cubed. And so then we can find the volume of the displaced water is going to be 0.5207 feet cubed. And now we go back to the truncated cone formula to try to find height, the depth of the water, the submerged depth, which is the draft of this floating body. But as we put this formula into our equation, there's actually two unknowns. The value h that we're trying to find, and then also the value big R, which is going to be the radius of the cross section right at the surface of the water. It's going to be some value between 4 inches and 8 inches. Right? We're not using the value 8 inches here because 8 inches was at the top of the wood, but the displaced water isn't all the way at the top. It's somewhere in the middle. So this big R, larger radius on the truncated cone, some value between 4 and 8 that we don't know what it is. So we've got one equation and two unknowns, which means we need a second equation. We need a geometric relationship between the depth and that radius at the surface of the water. And if we want to come up with a relationship between two variables, the best way to do that is to plot them against each other on x and y axes. So if I put depth on a horizontal axis and radius on a vertical axis, we can see that for this cone, at a depth of 0, the radius is 4, or at a height of 12, the radius would be 8. And that gives us a line, y equals mx plus b. We can describe this diagonal line as a function. The plus b part of it is going to be the y-intercept, which is the radius at height of 0. That's that 4 inches. And the slope of the line is simply rise over run. The rise is 4 inches from 4 up to 8, and the run is the 12 inches, the change in height. So we get a slope of 1/3. So the equation that relates height of this truncated cone to the radius of the cone is 1/3 the height plus 4. And we can double check the two values we know to make sure that this works. When height is 0, 1/3 of 0 is 0 plus 4. That gives us 4. When the height is 12, 1/3 of 12 is 4 plus the 4 makes 8. So it looks like this equation works. So we can plug this linear expression in as big R in the equation. And now the tedious algebra. Since we've got big R squared, you're going to have to FOIL this term out. We've got a 4 that we can distribute into this middle term. And of course, let's not forget these 4 and 8 are in inches, but that volume on the right-hand side is in cubic feet. So let's also convert that cubic feet to cubic inches to make sure that all of our units are going to match up again. We start grouping some terms together on the left-hand side to get the power of h's all together. We can move the 1/3 pi over to the right-hand side. And we're left with a cubic equation, which I'll plug into an online solver and find 3 solutions. Fortunately, it's not hard to figure out which is the right one because 2 of the solutions are imaginary, so it's definitely not them. And we're left with 9.15 inches for the submerged depth or the draft of this piece of wood. Does that answer actually make sense? We know the answer had to be between 0 and 12. If it were greater than 12, then that would be greater than the object itself. It would be sinking. An answer less than 0, of course, would make no sense. It would be floating above the water. But let's compare the density of the wood to the density of water and see if we can do a little bit better. So the density of the wood is about 2/3 of the density of water. And so you might expect about 2/3 of the wood to be submerged. The closer the specific weight is to the water, the more of it should be submerged. The specific weight being further away from water, closer to 0, would mean the less submerged, the higher it would sit up in the water. And so now the value we got was actually 3/4 of the total depth, right? 9/12. And this does make sense that it would sit a little bit lower because the cone is smaller at the bottom than at the top. So if we expect about 2/3 of the object to be submerged, then that fractional volume submerged would have to be over 2/3 of the way because it's skinnier at the bottom. So an answer of 9 inches it seems about right. When you get to the end of any engineering class problem, take 30 seconds and try to do this sort of analysis that lets you determine whether the answer makes physical sense. That's going to be the best way to catch mistakes and make sure that you're pretty close to the answer. You may not be able to tell whether your answer is perfectly correct, but you can catch a lot of mistakes this way just to find out that you're at least close. But the big question now, if I took this floating wooden object and started to tip it over a little bit, would it fall over to the side and flip upside down, or would it right itself back up? It's really counterintuitive. You would think that boats would want to have the lowest center of gravity possible, but a lot of times cruise ships actually try to have the highest center of gravity that they can get away with safely. And so we'll talk about why they do that in this next stability video.